So one thing I could do today is cover binary search. So that's a problem that'll be on the final exam, the third exam rather, and the final exam. But I could also talk about some of the problems that you have with the arrays lab. Is there any suggestions? Anything that you want me to look at, or should I just jump into binary search? Binary search?
Yeah.
All right. Let's take a look at that. So let me get just get some code to start with. Oops, too far. I don't think we won't need CMath. I'll take that out. So, oops. All right, so we've got the beginning here. So what binary search does is it lets you locate values in arrays or vectors. But the thing is, there's a requirement there. The values need to be in either increasing order or decreasing order. It's like a telephone book or dictionary. You know, the words are in lexicographic order. Right, they're in alphabetical order. So to look up a word or a name in a phone book or a word in a dictionary, you can sort of cut the dictionary in half and then find the right half to look in next and then the right half to look in next. You keep chopping in half. So that's what we're going to do. We're going to have a vector of integers, and which are in order, increasing order. And we'll write a function that looks for values using that same efficient algorithm of cutting the vector in half and getting at each pass, each loop, each iteration, we take half of all the data. It's like that dictionary. You know, you're taking half of all the pages each time. So you're always having the data that you're concerned with until you finally get down to a single value. And you say, well, is that it or is that not it? And if it's not it, then we didn't find it. If it's it, we found it. Of course, you could accidentally hit the value very early on in your search. So suppose you're going to look up a name that starts with the letter M in the phone book, and you just open it in the middle, and there's the name. So you hit it on the first try. So that's also a possibility. The worst case is if the name is not in the phone book, and that you have to do a thorough search and determine that the name isn't there. So we'll need some test code for that. Let's develop some test code. And maybe I'll use an array. Let's use an array. So we'll have an array A of integers. And we have some values, say -4, -1, 0, 3, 6, 11, 15, like that. So here, these are some values that are in increasing order. I just want to make sure that that compiles. There we go, that's good. So now what we want to do is is define this function called binary search, and call it with A and say, well, wait a minute, 1, 2, 3, 4, 5, 6, 7, 8. There's 8 values in A. So we want to look up in A, which has size 8. We want to look up the value, say, -1. And we could implement binary search in a number of ways. One way is we just want to know if -1 is in there. So we could implement the function so it returns true or false. Is -1 in there? Or another more common approach is to have the function return the position of the value that we're looking for. And I just realized that -1 is a very bad number to use. I'm going to use -2. It's not a very bad number to use, but it's going to be confusing. Because if we want to look up a number, say we want to look up the number 1, where is 1 located in the array? Well, 1 is not in the array. So how do you report that to the calling code? Well, the convention is to return a -1, because -1 is not a valid index. So by convention, programmers return a -1 to indicate that the thing you're looking for in the list isn't there. That's why I didn't want to use -1. I used -2, so I didn't want people to get confused between the -1 index and the data value -1 in the vector or the array. So let's implement it like that. Let's have this binary search function return an int, which is the position of k in A. Or -1 if k is not in A. And that's how I describe that. So the function returns an int. Return the position of k in A, or -1 if k is not in A. Let's implement this as a stub. We'll return 0. Actually, let's return, let's return 0. Now 0 is a valid position. So that would be the position of -4. So if we search for -4, our stub will return the correct position. So this should return a 0. So our stub will return a 0. It gives us the correct position of -4. We just wired it to work that way. Nope. This is integer k, integer size. There's the 0. Let's turn this into an assertion. So this value should return 0. Binary search is returning a 0. Let's assert that. I need the assert header, or cassert. So this code now will just print all tests passed. So we're building our automated tests. There it goes. So if we search for, not -4 this time, but -2, we should get position 1. If we search for 0, we should get position 2. See that? If we search for -4, we'll get position 0. If we search for -2, we'll get position 1. If we search for 0, we'll get position 2. That's position 2, 0, 1, 2. The third position is position 2. And so on. And I'm going to just hammer out the rest of the tests. And I'll test for everything. I'll be comprehensive. So 3, 6, 11, 15, and 16. And let's suppose we look for 17. If we look for 17, the function should return -1 to indicate that 17 is not in the array A. Maybe we want to check some others, like -1. That should return a -1. Now I'm going to check the edge cases here. If we're looking for -12, that's not in the vector or the array. So these are edge cases. This is past the end. This is before the beginning. This is somewhere inside. Maybe a little easier to look at. Of course, with our stub, the first assertion is succeeding, but all the others should fail. So let's just see that. There we go. Line 15 is the first failure. That should be the second assertion. I jump to line 15, :15 in VI. Then I'm right there. And that's the assertion that's failing. So now we've got our test code built. Let's look at implementing the algorithm. And what we're going to do here is we have to think about how do we split the array in half. You know, like the phone book, how do we get the book split into 2 groups of pages? So we're going to have some kind of midpoint, some integer. This is the midpoint. We're going to generate some midpoint to look at, and we're going to be inside of a loop. We're going to do this over and over again. So I'll just use a while true. It's an infinite loop, and we're going to look at this this midpoint, and then we're going to test it. You know, if A of m is the value we're looking for, if A at the midpoint contains the value k, then we're done. Then we'll return. Anybody know what we return? We have to return a position of k and a. That would be m, the midpoint. So we just found it, right? M is the position of k and a. A of m is k. And if we don't find it, we're in the loop and we don't find something, then we're going to end up returning -1. So I'm just going to put that down there. If we finish the loop, we don't find it. But maybe we'll take this out in a moment. I'm not sure yet. So we know the idea is we need to calculate this midpoint and look there. So the midpoint of what? So we have a range. The midpoint is going to look like this. It's going to be a start index plus an end index divided by 2. It's the average of a start index and an end index. So that's, like as we zero in, as we make the range of values that we're concerned with smaller and smaller, we're going to keep track of that range with the S and E. S is the start of the range, E is the end of the range. So that range is going to squeeze and squeeze down, get more narrow each time. And when we have those endpoints in the range, we can calculate M by taking the average of the start and end. That's how you get the midpoint. That's a midpoint calculation. So we need to declare this S and E. Let's take a look. So we have to have start. Initially, the start is going to be, the first position in the array, and the end will be the last position in the array, which is size minus 1. And so E points to a valid. E is will represent a valid position in the array. It won't be past the end of the array. If we just took size by itself, we know that's 1 past the last. If we use the size value as an index, it will be 1 past the last valid index. So we subtract 1 to get the last index. So we start with a full range. So S and E includes all the values in the array. And then inside this loop, what we do is take the average of S and E to get a midpoint. And then we check what's at the midpoint. Is it there? Is it at the midpoint? Now what happens if we find it? Then of course we return M. We're done. We found the location of K and A is at M. But if it's not, then we have to do another test. Else, well, if A of M is not K, maybe A of M is less than K. Now, if A of M is less than K, that means if K is going to be in the sequence, this increasing sequence of values, if K is going to be in A, it's got to be to the left of M. So, that means we want to adjust E. E becomes M minus 1. So we decided that K is to the left of this midpoint. So let's take our end, E, and slide it down and discard half of the range we're looking at, that part of the range that's bigger than M. And let's slide E down. And we don't bring it all the way to E. We don't say E equals M because we already checked M. We know it's not at M. If it was at M, we would have returned. So we're going to bring E all the way down to M minus 1. And we don't know what's at M minus 1. And of course, we have the other case. If A of M is greater than K, that means K is to the right of the midpoint M. So we're going to slide our start index forward to M plus 1. We don't set it to M because once again, we checked M. If it was at M, we would have returned there. So we're going to bring the start index up to 1 to the right of M, M plus 1. And now, there can't be anything else. I mean, this is impossible, right? So, see, this gets all possibilities. Either A of M equals K, or A of M is less than K, or A of M is greater than K. There's no other possibilities. So normally, in code, when you see this type of logic, normally this is omitted, and we just write it like that, because the only possibility at that point is that A of M is greater than K. That's it. So we normally write it like that. And this is, of course, more efficient. We don't have to perform another test. Right? It was an unnecessary test. We know for sure at this point, but you know what's a good habit to get into? And I'm going to put braces here. So we reasoned about that. We say, well, it has to be that A of M at this point is greater than K. It must be the case. And so a common thing to do is to put in an assertion rather than a test, because the test the unnecessary test consumes CPU resources, which we don't need to do. But maybe we reasoned incorrectly. So just to make sure that our reasoning is correct, we'll use an assertion. Now the assertion consumes resources too, right? So we don't want the assertion to run all the time. But the thing about assertions is when you do what's called a release build on a program, the assertions are normally ignored. So when you do what's called a release build, this is assertion. The code for that assertion will not be generated by the compiler. So you get faster running code. So these assertions are only used for development purposes. And I'm not showing you how to do a release build versus a debug build. I'm not showing you that, but assertions are turned on when we do a build. That's some fine tuning later on. Do that kind of thing. And maybe that's hard to read this code, so we could do this. Maybe to make it look a little more regular, spread things out a little. Maybe this makes it easier to read. I don't know. Is that a little easier to read? Now the thing that we need to do here is we've got to check the loop condition, because right now we have an infinite loop. So we never stop. See, S is getting bigger and E is getting smaller. So while S is less than E, then it makes sense to compute a midpoint. But let's suppose that S exceeds E. That doesn't make sense anymore. We didn't find it. But what about if S equals E? Is it possible that S could equal E? It could be. After we do something like this, say we set E to M minus 1 and E becomes S, we still want to do this test here. So we want to check for S less than or equal to E. And let's suppose that S hits E. Let's suppose that S and E. So we're zeroed in on a single value. S and E are the same. What's the average of S and E if they're the same value? Well, just the same thing, right? The average of 4 and 4 is 4. So M is both S and E, if S and E are equal. So let's assume we're near the end of the loop. S and E are equal. So M is, say, S, and then we check A of S. Let's suppose we find it, of course, and we return M, which is S or E at that point. But let's suppose that it's not, the value K is not in the array. Then when we check this, A of S, or E, it's not equal to M, so we go to the next one. So we check, is A of S less than K? And so that might be true. Or if it's not true, then we'll go into the else clause. In any case, we're going to make we'll either make E smaller than S, or we'll make S bigger than E at the last, iteration of the loop. Now, that means that S now exceeds E, so the loop condition is false. And then we'll exit the loop and return -1. That's binary search. Let's see if we got it. We did not get it. Assertion failed. Line 27. We messed it up. So what's going on here? When we look for the first value, it does not return a 0. What did I do wrong? So the size is 8. What is going on? You know what? We got to do some debugging. Let's take a look at what S and E is. How could this be? So that is not 0. Oh, this is a mystery. All right, let's see what happens here. So we start at 0, 7, that's S and E. And then we compute the midpoint. Well, I can see what's going wrong already. We're trying to find -4, right? So S and E are 0 and 7. And we say, well, let's compute the midpoint. So we want to look at, and the midpoint is, you know, like here somewhere, right? Like this, somewhere, one of these. And we compare it to -4. And we say, well, no, -4 is too small. And look, we're going up. We moved S larger. We're supposed to make E smaller, right? So the range should be not 4 to 7, but 0 to 4, or 0 to 3. So we're going the wrong direction. So the problem is here. Oh, K is to the right of M. You see the mistake I made? This is if K, this should be if K is smaller than A of M. So maybe if I write it like this, I want K to be smaller than A of M. I made a mistake there. K should be smaller than A of M. When K is smaller than A of M, then let's move E to the left. So that's my mistake. I'll take out that trace statement there. I still got it wrong. Which one was it? Oh, look at that, line 17. Oh, I got that wrong. This should be K shouldn't be less than A of M. K should be bigger than. That's our assertion. Just that the assertion was false. That's all. Let me get it. There we go. Just had the wrong. I flipped around this inequality so it was correct, but I didn't do the same for here. Also, just visually, it helps if I put the K to the left of A of M, and then I see an I use less than there. So that's it. That's binary search. And what I recommend, this is what I recommend to you, because this is confusing, right? But it's not that tough. You know how to search through a dictionary. That's easy. So you know the algorithm. I mean, clearly you know the algorithm. The problem is, how do you express what you know naturally How do you express that in code? That's the problem. That's what you need to practice. Once you get good at that, you can come up with all kinds of algorithms to do things. You know, like algorithms to control robots, to make them walk across the room and pick up balls and, you know, and put them in baskets, all kinds of stuff you can do once you get good at coding up algorithms. Now, so this is what I recommend. Don't memorize this algorithm. Practice coming up with it on your own. And it's not, you're not going to do it fast. I mean, look how long, what is it, 12:30, right? I've done this a million times. It still took me a half an hour. But practice coming up with this on your own, thinking it out. How do you sort of relive that discovery experience as you go through and code it out? And then, you know, if you're stuck, of course, you can look at my code, or you can look at another code on the internet. You can find there's some nice presentations on binary search, I understand, that students from previous quarters have found and have viewed. But don't just memorize the algorithm. Practice deriving. Just like today, you know, I did not produce this out of memory. I mean, I had some memory of some features. I knew that I wanted to do this because I used to have E. You can do the algorithm differently. Like E could be one, you could set E to size, which is one past the end of the range. And you could develop the algorithm that way. But the code doesn't turn out to be as compact as this. And I remember that, okay? So I'm applying some memory to coming up with this problem. But if I set E to size, I can still come up with it. I can still come out. And I didn't remember that in previous classes. I was always, it's sort of arbitrary. Is E going to be, the end of your range, or do you want it to be one past the end of the range? It's a bit arbitrary at the beginning. You don't know what the benefit is. But it turns out if you set E to the end of the range, the code can be simpler to express. And I just didn't remember that. But now I remember it because I've done this so many times. So I picked the easier route. But so as you go forward, you just have to practice this. And this is kind of like the beginning. Actually, the problems that we're doing here, like my maximum, append vector, these are linear algorithms. So you have to do, like for instance, count occurrences. You have a vector, and you're looking for how many times does k occur in V. How many k's are there in V? If k was 3, how many 3's are in V? V could have 1,000,000 numbers in it, but there's 10,000 3's. We're going to count those 3's, and then I'm going to return the value 10,000, or 10,000 3's in that vector of 1,000,000 numbers. So that's a linear processing problem. You have a loop, and you look at the value at the first index, then the second index, and the third index, the fourth index, and each time you say, is that k? Yes, okay, add one to my counter. Look at the next one. Is that k? No. Okay, look at the next one. Is that k? Yes. Oh, increment my counter. Okay, go to the next one. You see that's a linear algorithm. And this exercise here is focused on practicing coming up with linear algorithms. Obviously, if I asked you to count, if I gave you a list, and wrote it on the board here with the numbers, I say, how many times does the number 3 occur in that list? I mean, you would know what to do, right? You would look at the first one and you'd count them. You'd go from the left to the right, or the other way, it doesn't matter, but you would use some kind of process, especially if the list was long. You would have a process. Your finger would go across the numbers and counting one. Each time you hit a 3, you would count. So you know how to do it. All of these problems you know how to do. You could do it as a human. And but the problem is, how do you express these simple procedures in code? And that's what you need to practice. You got to practice these. Don't just memorize the answers. Don't look at, what I present or what Jaron presents to you, or look up the answers or get them from your friends. You can do that too if you want. You can look at it, but remember, put that aside and derive the code on your own. And you've got to practice that. It's like lifting weights. You've got to build up some muscles. You got to keep working at it. You got to go jogging. You run a half a mile for a few days, and then you're starting to run a mile now, right? So you got to practice it. It's very much like practicing. Learning to play the guitar, for instance. You got to practice the thing. So you got to practice these. And be wary. Don't do too much memorization. You can do a little bit, but that's not where it's at. It's not about memorizing things. And I'm going to do my best to make memorization fail in the exam. The problems will be very similar to these, but I don't want you to get the problem by memorizing an answer. I want you to get the problem by having developed that ability to come up with a solution. All right. So anyway, that's binary search. Let's look at this. And there's a whole bunch of things. There's also linear search in here. These are going to appear on the exam. Linear search is where the array or the vector, the numbers are not in order. So they're in some random order. So binary search only works if the numbers are either increasing or decreasing. So if they're randomly distributed throughout the list, then you have to look at each one. And that's called a linear search. So if the size of the vector is n, you've got to look at n things. But a binary search, the size of the vector is n. You only have to look at, in the worst case, log n things. Log base 2 of n things. Because you're cutting, so what you're looking at each time, you're cutting the thing in half. So you're discarding a lot of values that you don't have to look at. And it turns out that the number of iterations that your loop has to go through is log n at the worst case. I mean, you might hit the number, if you're lucky, you'll find the number right away. But in the worst case, you're going to chop your data in half log n times. So that's the benefit of binary search, and there's a huge difference in runtimes, by the way. I mean, binary search is immensely faster than a linear search. So those two things, those two algorithms, you really need to have understood completely. Now with the binary search in the exam situation, oh here, look, this is the one we did today. I just showed you this one. I could say, assume that the values are in decreasing order, then code it up for that. Or I could say, well, instead of an array, here's a vector. Implement the function so that you're using a vector rather than an array. All of those problems are very similar. Oh, there's another variant that I do. Instead of returning the position of k in A, just return true or false. Is k in A or is it not in A? Return true or false. That's another variation. So there's lots of, that's like, 8 variants on the problem. Okay, I'm going to give you one of those 8 variants. Either it's a vector or an array, returns an int position or bool, or it's increasing or decreasing in sequence. Those are the different variants. That makes 8 different possibilities, right? 2 to the 3. So there's 2. There's 3 independent choices between 2 choices. That's 2 to the 3 possible problems I could state. So anyway, that's that. Here's another exercise. Just briefly talk about this. Guess the number game. Well, wait, I don't want to go too fast here. Let me slow up. Are there any questions about binary search or, my suggestions on how to study to learn the material? Anything? Yeah.
Just a clarification on the homework number 2. It says that you want doubles. Is that correct?
Right there?
Yes. For the 2D array.
Oh, this should be double. Yeah, I spelled that wrong. Yeah, I'll fix that. And I modified these a little bit the other day. I want you should write test code for each of these problems. Oh, sorry, I didn't modify this one. I modified this one. I added statements saying, provide test code. And in some cases, the test code is a little tricky. So here, for instance, here I provided the test code for you. So use this. But actually, I didn't test the test code. So let me know if I got the test code wrong, okay? And it's very easy to make a little mistake. Here's another chunk of test code I gave you here. Use the following to test this. There aren't good tests for these two problems, so I just created some version of that. These are going to be the kind of problems I'll ask on the exam. I'll give this problem to you directly, and you'll have to code it out. Implement this function, like flat, right? Come up with that in the exam. So these are all relatively easy problems. The binary search takes more time to think through. It's harder. And then we have one more algorithm to look at, which is sorting. And this is harder than binary search. So, linear processing, linear search is like the beginning of algorithms. And then binary search is one step sophisticated. And you're starting to think about efficient ways of solving problems computationally. And then sorting, that's where you take an unordered sequence of values and rearrange them so that they're either increasing or decreasing in sequence. It turns out it's a very important problem. When computers were first invented, this is what they had to do. They had to do searching, like binary search, and they had to do sorting. It was just, when computers were first created, those are the algorithms that were immediately needed, and those were solved, and then those were studied. And this particular problem of sorting algorithms has been studied extensively. And it turns out that some sorting algorithms are much better than others. And the sorting algorithm that we'll be coming up with will be one of the bad ones, because they're the easiest ones to come up with. But it turns out there's better ones that if you take later courses, then you'll learn about faster, more efficient sorting algorithms. And it can get pretty complicated to study, the mathematical sort of characterization of those algorithms, why one would be faster than another one. It can get pretty deep and opens up into theoretical computer science, actually. That's the beginning of theoretical computer science, studying algorithms and their efficiency. So, is there anything else? I mean, we have quite a bit of time left if you want to do something else. Maybe you've had enough. Is that enough? More? All right, let's do more. Let's do more. How about one thing we could do is we could start looking at some of these practice problems here. I'll make some. Pick one. Pick one of these practice problems for me, and then we'll look at it together. Okay. So let's. Yeah, take a look at those problems and see if there's one that you'd like to look at. Which one do you want to look at? Is unlucky? Okay, no suggestions. I'll just pick that one. So here's the function signature. So I'm going to say, implement that function. Now, on a test, you would just, give a short answer like that, okay? But I'm going to just go through the whole process and show you how to code it up. Because when you're practicing, you should be coding. Now, coding is really important. So I have this function called isUnlucky. We're passing a vector. Is the vector unlucky? So we're going to write a stub. We're going to return true. Yes, it is unlucky. So in the test code, we'll create a vector. And we're going to push back some data. So remember, the vector, when you create the vector initially like this, it's empty. So we're going to have to add data. So we push it onto the back of the vector, calling pushback. So we'll push back, say 3. We'll push back 7. Push back 1. Push back 11, push back, say, 13. Maybe that makes it unlucky. We don't know the definition yet of unlucky, so we're going to do this. We'll have an assertion. So it is unlucky. V V should be unlucky. But what is we don't know what unlucky is yet, right? So I can make all kinds of definitions for that. So you need to be flexible about that. There's no such thing as an unlucky vector. We're just going to make believe, the number 4 in a vector makes it unlucky, something like that. Oh, let's see, run the test code. It's just a stub, should work. But see, now we need to debug.
That's a vector header.
Yeah, exactly. Thank you. Thank you. The vector header is missing. All right, now let's read what it says here. Implement a function that determines if the unlucky number 13 appears in a vector. The function returns true if 13 appears in the vector at least once. Otherwise, it returns false. This is a very simple one. So this is a linear. So we need to look through the vector v. If we find a 13, we know that right there on the spot it's unlucky. Let's return true. Otherwise, we have to look at every number. If we don't find a 13, we're going to return false. So at the end of the day, after the loop, we're going to end up returning false. We didn't find it. So we need to iterate through the vector linearly. I think iterate implies linear. So we're going to have int I 0. We're going to take I is going to be the index in V. So start at 0. That's the first position. I needs to be less than v dot size. And then we increment I at the end of the loop. Now if we find it at I, if we find that v of I equals 13, then we know right there that we got an unlucky vector. So that's it right there. So this is a simple one. Let's test, so this is unlucky because there's a 13 there, isn't there? I'm just going to do 2 tests here. I'm going to create a vector 3, 4, 1, and 11. Is unlucky should be false. But then when I push back a 13 and call is unlucky after that, it now should return true. So there's a test right there. There we go, got it. Well, maybe, let's change the problem. Maybe the presence of a 7 cancels the bad luck from a 13. So maybe the problem is something like this. V is unlucky if it contains a 13 and no 7s. So V is unlucky if it contains a 13 and no 7s. How would we do that? It's another example of a problem that I could give you. How would you do that? Actually, I haven't given this problem, and it's a little harder than the variance that I've given before on this problem here. Let's think about what we need to do. Well, I think maybe the easiest way to go about it is to declare a Boolean variable called unlucky and set it to false. We're going to say it's not unlucky. We're only going to set it to true if we find a 13. So if we happen to find a 13, we're going to set our unlucky Boolean variable to true. We found a 13. So unlucky, it's going to be unlucky. Well, we don't want to return yet because maybe we found a 7. I'm going to do it inefficiently first, and then I'll show you how to do it efficiently. So we're going to go through the whole thing all over again. If we find a 7, then unlucky is we're going to set it to false. And then at the end of the day, we're going to return this Boolean variable unlucky. But this is wasteful. First of all, do you see what I'm doing here? So we start by saying it's not unlucky, but if we find a 13, we set it to true. It's unlucky. But wait a minute, let's check for 7s. If we find a 7, we're going to set unlucky back to false again. But this is wasteful. We have 2 loops. And we could have done it like this. In the first loop, let's check for the 7. But I'll show you some faulty code. If we find a 7, we set unlucky to false. And then we don't do the next one. But what happens if we have a vector of all 7s and a 13 at the very end? When we hit the last value, we're going to set unlucky to true and then return true. So that won't work. Thing is, a 7 is gold. It means the thing can't be unlucky no matter how many 13s are in there. So we're just going to return false if we find a 7 right off the bat, just like that. Now we don't have to worry about setting the variable unlucky to true later on, and then returning that. Does that even work? Let's see. Oh, it's faulty. What did I get wrong? Oh, because the test case is not right. So this should be, is unlucky should be false. Right? This is the test code for the other problem. So we really need to change this around So here is unlucky is false. If we push back at 13, then is unlucky, oh, but I got a 7 there, don't I? Now, is unlucky is true. So to be unlucky, we have to have a 13 without any 7. At this point, we have a 13 with no 7. We add a 7. Unlucky is false. We add another 13. Unlucky is still false. Let's see if that works. That should be the correct test code. There we go. One problem with using automated tests is you have to debug the test code as well as your regular code. So there's an argument against that because, you know, let's not use an automated test because we have no tests for the test code. You know, the test code also has to, so we want to use automated tests to improve the development of the software. But if the automated tests have flaws in them, then that's going to send us in the wrong direction. And also take a lot more time. But I think in general, test code is good. But you do have to be careful to get it right. And it does take extra time to write. So this is one way. There's other ways we could do this as well. But I think this is one way to do it. So just I'm showing you variations on the problem here. Any questions about this? Okay. Let's take a look at another one really quickly here. First, I'm going to check this. It should be the simple. On the exam, this is what you don't need to use test code or unless I ask for it. You don't have to give the function definition at the top, you know, the function signature. Just show the loop and the return values like that. Here I'm asking for test code. And I say make sure that, make sure you test every statement. So you want to test that you want to, you know, have is unlucky return false and true both. So you want to make sure you have 2 tests there. Is strictly increasing. This one is tricky. Flatten. This one is, this was in our assignment, wasn't it? This flatten. How about this one? Is strictly increasing. This one is a little tricky. Let's do this one. So is V strictly increasing? Let's return true. Yes, it is. That's our stub. So it's called a predicate function. The word predicate function, the term predicate function rather, predicate function means, it simply means it returns true or false. So the return value is a bool. So this function checks whether a vector of integers contains values that are in strictly increasing order. For instance, this is in strictly increasing order. But this one is not, because there's 2 6s next to each other. So the second 6 needs to be larger than the first 6. So that fails the criteria. Well, we'll use that. Let's see, -2, 4, 5, 6, and 8. All right, so this one is good. Is strictly increasing, should return true. But the other example, 1, 2. Let's have another vector. We'll call it W. In this example, it's 3, 4, 6, 6, 9. 3, 4, 6, 6, 9. And this is not strictly increasing. So the word strictly means it's always going up. It never levels out. Of course, it doesn't go down. That would be decreasing. So strictly increasing means it doesn't level out. So we don't want two 6s next to each other like this. It's increasing, but not strictly increasing. And that's a terminology from math. Let's see if that compiles. Of course, it won't run. The test cases are not. I mean, we didn't function. We only have a stub here. So now let's go ahead and implement this. So I think that my hunch is we need a Boolean value. No, maybe not. No, I take that back. Look, what do? We need each value. If it has a value coming after it, it has to be smaller, strictly smaller than the value coming after it. So the number of position 3 must be smaller than the number of position 4. So we're going to look at these pairs. We want to make sure that every pair that we look at, the first value is smaller than the second value. We're going to have a loop. But we don't know how far we go. So we're going to look for these pairs. Now, let's suppose we start at the first pair, and we have, we're going to compare v of 0, is v of 0 should be less than v of 1, right? So if v of 0 is less than v of 1, what do we do? Well, nothing, because that's the way it should be. We can't make any conclusion. We got to keep looking at the next pairs. But the key is to realize that we want to be looking for this condition. We want to look for the fail condition. If v of 0 is greater than or equal to v of 1, then we have a problem. We don't have to look at any other pairs. We found a bad pair. That's good enough. It's not strictly increasing. So right then and there, we just return false. That's the trick that you have to realize when you're working on these type of problems. And you'll see this. This is a theme that's going to recur as you work through all these problems. We found a condition with one instance, one pair, and then we can make a conclusion and return the true or false right there on the spot. But we can't return true right on the spot, because to return true means everything is increasing, but we have to look at every pair first before we return true, which is down here. Oh, by the way, we don't want this to be 0 and 1. We want this to be I and I plus 1, right? Oops. If the value at I is greater than or equal to the value in the next position, I plus 1, then it's not strictly increasing. Let's return false. We're bad. Otherwise, we don't want to have an else. This is a typical mistake. This is a typical mistake. Do you see the mistake? We can't return true here because we haven't looked at all the pairs yet. Finding one good pair is not good enough to conclude that all the pairs are in the right order. But that's a very common mistake. You know. Half of you are going to make that mistake. So now the problem is, look, this is the normal loop. When I goes all the way to the last position, which is size minus 1, okay? And when I hit size, when I hits the value v dot size, the size of the vector, we're done with the loop. So I will never reach the one past the end of the vector. I will hit, in the common loop scenario, which I have written here, I takes the value of the last position in the vector. Is that okay? No, it's not okay.
Which compared to a value outside of the.
Yeah, because we're looking at I plus 1. Well, I can't be at the last position because I plus 1 doesn't make sense.
Which would be size minus.
Exactly. That'll do it right there. So that's that one. And so that's a problem I ask a lot. You know, if it's not on the next exam, it'll be on the final. So probably, I mean, just based on what I've done in the past, I usually include this problem on the exam. But I might ask, is strictly decreasing? Or I might say, is just increasing. I may not say strictly anymore. I may say, is increasing. So you're going to, you know, if it was, is increasing, is this increasing, then we just have to look for the case when v of I is strictly greater than v of I plus 1. Then we got a failure. Because if v of I equals v of I plus 1, we're okay. Because, you know, we didn't decrease, we didn't go down. Actually, this is not well defined. Is increasing, is non-decreasing. I think that's what the math people say. They would say v is non-decreasing. So I might say, whoops, what did I do? Is non-decreasing. So it's okay to be flat, to flatten out, but it's not good to go down. So if we go down here, then it's bad. We got a bad vector, so we're going to return false. So this is I think that's a standard term they would use in math. They would say non-decreasing sequence. And of course, this all of these tests would change. So that kind of those kind of variants on this problem I may ask on one of the exams. Okay, I think that's it then, right? We're all set. Any questions?